All right, let's look now at section 5.7 and talk about the inverse trigonometric functions, and we're going to begin with differentiation. We'll talk about integration in the next section. So let's remind ourselves of the definitions of the inverse trig functions, and let's begin with a regular trig function. Remember that the trig functions are all periodic, with period either pi or 2 pi. Some of them have a longer period than others. Here is a quick sketch of the sine function. And of course, that's not the entire sine function because it continues on forever and ever and ever. That's 0 and pi and 2 pi and negative pi and negative 2 pi and so forth and so on. Now, here, the domain of the sine function is infinite, but the range is between -1 and 1. All right. Now, here, this is not a one-to-one function. Clearly, all right, there are lots of different x values which give me the same y value. For example, just the y value 0. If x is equal to 0, the sine of 0 is equal to 0. But the sine of pi is also equal to 0, and the sine of 2 pi is equal to 0, and the sine of 3 pi and 4 pi and so forth. So clearly that's not a one-to-one function. But thinking back to our basic algebra, for a function to be invertible, for us to be able to have an inverse, we have to have a one-to-one function. So what we do is, instead of looking at the entire function, we take a look at only a portion of it. We look at this portion from x equals to negative pi over 2 up to x is equal to positive pi over 2. And even though the entire function is not one-to-one, this portion of it is. If you restrict ourselves to this part of the function, then that is one-to-one. So because that's one-to-one, that means we can invert it. So that means that if I have a function like y equals the sine of x, I can now, at least for this part, I can define a function that undoes this sine function. We can call that the inverse sine, also sometimes called the arc sine, so that it looks like this. If I take the arc sine of both sides, the arc sine of the sine of x will give me just x. And over here, I end up with the sine inverse of y, like this. So that's how we define that inverse trig function. But note that we are not defining it for all values. We're defining it only for these values in here. So what that means is this is only defined when, well, let's see, these y values go from -1 to 1. So here y is going to go from -1 to 1. So y is an element of, it's contained inside of the interval from -1 to 1. And x, well, x is the domain. And you say, well, that's all real numbers. Well, that's the domain of the original sine function, but we restricted it to negative pi over 2 to positive pi over 2. So x is an element of this interval from negative pi over 2 to positive pi over 2. So here we define the inverse trig function, in this case the inverse sine function, as the operation that, when composed with the sine of x, gives you just x. Or, to give a more precise definition, rather than say, oh, it's the thing that cancels sine, let's give a more precise definition in terms of the original trig function, in this case the sine. So definition, y is equal to the inverse sine of x. That is equivalent to saying that x is equal to the sine of y. So saying the inverse sine of x is equal to y is the same as saying that the sine of y is equal to x. That's kind of what this says here, right? Yeah. Now, of course, that does require a restriction. So here we're going to say, okay, we're going to restrict our values to where here the focus was on the original sine function. So we said sine of x. In this definition, the focus is on the inverse sine. So here they're saying sine inverse of x. So it's going to be backwards from the way I wrote it here. That's why I said we're going to be a little more precise for defining the inverse sine function in terms of the sine function. In other words, we're going to focus on the inverse sine. So here, it's the same values, but they've made a different choice than I have. So I'm going to go ahead and stick with their choice. I'm going to say, okay, since we're focusing on the inverse sine, we're going to say x is the argument of the inverse sine. And so x is bound between -1 and 1. So where x is an element of the interval from -1 to 1, and y is an element of the interval from -pi/2 to +pi/2. Okay. All of the other trig functions and their inverses are defined in a similar way. We have y is equal to the inverse cosine of x, and that's true and that's equivalent if and only if x is equal to the cosine of y. This one will also be restricted to having x values between -1 and 1 inclusive of those endpoints, and y between 0 and pi, again inclusive of those endpoints. Y is equal to the inverse tangent of x is the same as saying x is equal to the tangent of y. Y is the inverse tangent of x if and only if x is the tangent of y. And here we restrict our value of x. In this case, it's not actually going to be restricted since the range of the original tangent function is infinite. That means that the domain of the inverse tangent function will have that property. So here, x is in the interval from -infinity to infinity. Thinking back to algebra, when you invert functions, the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. They flip around. So here, the domain of the tangent is every real number except for where the asymptotes are, but the range is every real number. Okay, so if the range of the tangent is all real numbers, the domain of the inverse tangent will also be all real numbers. And here, y is going to be restricted to be between -pi/2 and +pi/2. The difference is here it won't include either of those endpoints because, again, that's where you'll find an asymptote. Just like that. Y is equal to the arc, let's do this one. So the arc cosecant of x, inverse cosecant of x. Y is equal to the inverse cosecant of x is equivalent, is true if and only if x is equal to the cosecant of y. And here that's going to have us restrict ourselves to the absolute value of x being greater than or equal to 1. And it's going to have us restrict us, let me go ahead and write this the same way I've been writing the other ones. X is an element of the interval from -infinity to -1, union with the interval from 1 to infinity, anywhere in either of those intervals. And y is going to be contained in the interval from -pi/2 to +pi/2. With an exception at 0, because we're going to have an asymptote there. So I guess I should write this way. We want everything from -pi/2 up to 0, union with everything from 0 up to pi/2. And again, because at 0 you're going to have an asymptote. The arc secant, the inverse secant function, is defined as y equals the inverse secant of x if and only if x is equal to the secant of y. And that's going to have a restricted domain where x is going to be, in fact, it's the same as this one, -infinity to -1, union with 1 to infinity. And y is going to also have a single exception for the case of its interval, of its asymptote in the interval. So this will be everything from 0 to pi, with the one exception being at pi/2. Right in between the interval, you'll have an asymptote. To pi. And let's see, that's 5, so we're missing the inverse cotangent. And y equals the inverse cotangent of x is defined by saying that x is the cotangent of y. And again, we're going to have a restriction. Here, just like the tangent, the cotangent has an infinite range, which means that the inverse cotangent, just like the inverse tangent, will have an infinite domain. We'll have a domain made up of all real numbers. The range is going to be between 0 and pi, and it won't include either endpoint, just like the tangent, because again, you'll have asymptotes there. So here y is an element of the interval between 0 and pi, not including either one. So all of this should sound extremely familiar. These are the same definitions that you have in trigonometry for the inverse tangent, inverse sine, inverse cosine, inverse cotangent, inverse secant, and inverse cosecant. The difference being that in trigonometry, this is explored slowly over the course of several hours, over the course of several sections in the textbook. Here we summarize the results in a few minutes. Right? So here we define our inverse trig functions. Now, in later sections, we'll be using trigonometric functions and their inverses to our benefit. One of the things you may remember from trigonometry is that every trigonometric function can be written in terms of every other one. You have an expression that involves sine, you can use a Pythagorean identity to write it using cosine. If you have something involving sine, you can use the reciprocal identity to write it in terms of cosecant. Or, what if I want secant? Well, then use the Pythagorean identity to go from sine to cosine, and then from cosine to secant. Right? And, well, we have identities to tie together just about any expression in terms of any function to some other expression of some other function. That's going to be extremely useful in later chapters in this course because one of the limitations in calculus is being able to find an antiderivative. The fundamental theorem of calculus tells us if we want to find an integral, we can find it by finding the antiderivative. And then once we have the antiderivative, we can evaluate at the endpoints and everything's good. The problem is finding that antiderivative in the first place. One of the reasons it's so difficult to find an antiderivative in general is because your integrand might not be written in a way that's useful. You may not be able to perform a nice substitution. Now, some of the techniques that we'll cover in this course will involve us learning things besides just the most basic integration techniques. We'll learn some more advanced ones. But the other thing that we're going to need to do is, even with those advanced techniques, sometimes the integrand is just too complicated to work with the way it is. That's where trigonometric functions and their inverses come in. If you can take an expression, write it in terms of trigonometric functions, then you can rewrite it in any way that is convenient. After all, if I have a function that I'm trying to find the integral of, trying to find the antiderivative, and it involves tangents, and I just can't do it. I try and I try every technique that I know, and I just can't do it. Well, maybe tangents just not going to work. Okay, then write it in terms of sine and cosine. Oh, maybe now it's easy. That's going to be the main advantage. In several problem types, we will note that we will simplify algebraic expressions by rewriting them in trigonometric forms. Generally speaking, trigonometric equations are more complicated than algebraic expressions. A polynomial is easier to work with than a trigonometric function and a trigonometric equation, but that's only if we're trying to solve an equation. If we're trying to integrate, if we're trying to find an antiderivative, oftentimes what makes these complicated, namely the fact that they can be rewritten in many, many forms, is what's going to be necessary to help us find the antiderivative, the integral. All right? So let's go ahead and remind ourselves of a few other properties of trigonometric functions as they relate to their inverses, because again, we'll be using these to our advantage. Trigonometry, when you first learn it, is harder than algebra. But now that we have both of them as something that we know how to use, it's going to turn out that sometimes trigonometry is preferable. It's going to be easier. So as an example of something from trigonometry, you'll notice there's no calculus in here at all, but we'll be using this kind of example in just a moment to do some calculus. Let's go ahead and evaluate the following result. Let's say I wanted to find the cosine of the arc tangent. You'll notice I keep saying arc sometimes. That's just another way of saying inverse. So as a quick note on notation, if I say if I write this is read as sine inverse of x. Sine inverse of x. If I write this This is read as arc sine of x. These mean the same thing. These are just different notations for the same thing. These are interchangeable. So if I write this, I should say tan inverse, tangent inverse. However, I could also have written it the other way. I could have written it as arc tangent. And so sometimes we'll use these interchangeably. They're different notations, but they do mean exactly the same thing. So here, if I say inverse tangent, or if I say arc tangent, that means exactly the same thing. It's just two ways of writing it. It's like saying I have x to the 1/2 power or square root of x. Those are different notations, but they mean the same thing. Same thing for those. All right? So here, the question is, we're going to find the cosine of the arctangent of, I don't know, let's give a perfectly terrible number. Let's say 3/17, because why not? Okay. Now, obviously, one thing we could do is we'd come over here and do this, right? We could say, okay, 3/17, take the arctangent, and then take the cosine, and then we're done, right? But, well, what's the fun in that, right? But also, because in a moment, these aren't going to be numbers. So here, let's go ahead and see how we would do this without just typing it in somewhere. And again, this is something you have seen since trigonometry, but that might have been a few semesters ago. So let's remind ourselves of how this works. When we say we want the arctangent of a number, we're saying that. We're saying we want that value of y. Okay, but what is y? Well, y is something I can take the tangent of. So you're saying y is an angle. That's right. Y is an angle because I can take the tangent of it. So the arctangent of x is an angle. This thing right here, arctangent of 3/17, this whole thing is an angle. So because it's an angle, I can draw it inside of a triangle. So let me draw a right triangle. And let me take this angle, and I'm going to call it y, just to keep up with the notation that I have over here. And I'm going to say, okay, there's my y. And there it is, right? I have the tangent of that y is equal to x. Or in my case, the tangent of this y is this 3/17. Right? Because after all, that's what our definition says. When I say I want the arctangent of that number, what I'm saying is I want some angle. Which angle? The angle whose tangent is that x number. So what I'm saying is that y has a tangent that's 3/17. Well, remember, if the tangent of that angle is equal to 3/17, that means that one way of interpreting the tangent of y is the quotient of the side opposite divided by the length of the side adjacent to y. So here, this side would be 3 units in length. The side opposite would have unit 3 length, and the side adjacent would have 17 units in length. But now by the Pythagorean theorem, I can fill in the third side. All right, I can say, okay, well, then that means 17 squared plus 3 squared is equal to c squared. After all, c is my hypotenuse. So I can square 17. That's going to give me 289 plus 3 squared is 9 is equal to c squared, which means c squared has to equal to what? 298. So that means that I can take the square root of both sides, plus and minus the square root of 298. And since we know that c is the length of a hypotenuse, well, it can't be negative. So that means this has to be positive square root of 298. Just like that. So now, when I say I want the cosine of the inverse tangent of 3/17, I'm just saying I want the cosine of the angle, that angle being y. Okay, so the cosine of the inverse tangent of 3/17 is equal to the cosine of, this whole thing is just that angle y. Oh, but now I know how to find the cosine of an angle y if it's inside of a right triangle. The cosine of the angle y is the length of the side adjacent to it divided by the length of the hypotenuse. Just like that. I can go ahead and rationalize that. Multiply top and bottom by 298 square root. Just like that. And so this gives us a result of 17 root 298 over 298. And there we go. That's the cosine of the arctangent of 3/17. It's going to be 17 root 298 over 298. Interpret this as an angle. Draw it out. You don't have to draw it out. If you can do this part in your head, that's fine. But since you guys can't see in my head, I draw it out. Once you interpret that angle and have the appropriate side lengths, you can then use the angle here to find this function of that angle. Keeping in mind that the sine of an angle can be thought of as the ratio of the length of the side opposite divided by the length of the hypotenuse. Cosine is the adjacent length divided by the hypotenuse length, and tangent is the opposite length divided by the adjacent length. And of course, secant, cosecant, and cotangent are just the reciprocals of those. So give this a try. Let's say we're going to have you take let's say you want to take the sine of the inverse cosine, and you say, oh, well, can we just plug it into a calculator? Here I'm not going to give you numbers. We're going to have this be, let's just say x. Give that a try. As a little hint, keep in mind that x is the same as saying x over the number 1. X is like saying x over 1. So give this a try. Go ahead and interpret this as an angle, and then take the sine of that angle. Pause the video to give yourself as much time as you need, and once you have a result, go ahead and unpause and we'll go through it together. All right, so let's take a look. I'm going to say the inverse cosine of x. Well, that's an angle. Okay, so here, let me go and call this an angle. And we can use whatever letter we like. I'm going to continue to use y just like I did in the last one, but you could say theta or whatever you like. The inverse cosine of x is some angle y. In fact, let me even write that. It's an angle y. Okay, well, what angle is that? Well, it's some angle that's situated inside of a right triangle. It's one way of defining the trigonometric functions. I'll use that angle there. It could have been either of those. And now I say, okay, well, what angle is it? Well, by definition of the inverse cosine, it's the angle whose cosine is x. Or in other words, x over 1. Okay, well, the cosine is given by the length of the side adjacent to the angle divided by the length of the hypotenuse. So that's the length of the side adjacent, okay, divided by the length of the hypotenuse. That must be 1. So now by the Pythagorean theorem, I can find that third side. Okay, well, let's see. The short side squared plus here, that's, I'm just going to put a little blank there, squared is equal to 1 squared. A squared plus b squared is equal to c squared. Okay, so then that means that I can go ahead and subtract this to the other side. And that'll give me that blank that I'm still looking for, squared, is equal to 1 squared is just 1, minus x squared. And now I can take the square root of both sides. Okay, so if I take the square root of both sides, that blank that I'm looking for is plus or minus the square root of 1 minus x squared. Now, of course, that's the length of a triangle. It can't be negative. Okay, so that must be positive. So square root of 1 minus x squared, just like that. And so the angle inverse cosine of x is that angle there inside of that triangle. So now if I want to find the sine of the inverse cosine of x, that's really just saying I want the sine of the angle y. Oh, well, there it is. And the sine is given by the length of the side opposite divided by the length of the hypotenuse. So that's going to be the square root of 1 minus x squared divided by the hypotenuse of 1. And of course, dividing anything by 1 is just itself. So here we can write that as just the square root of 1 minus x squared. And there we go. The sine of the inverse cosine of x is the square root of 1 minus x squared. So now for the next thing we're going to do, we're going to need to recall a result that we see in Cal 1. and that has to do with finding the derivative of an inverse function. And that is, let f and f inverse be inverse functions. One is the inverse of the other. To find the derivative with respect to x of f inverse, you know what? Let me use the prime notation because it actually does look a little nicer in prime notation. So to find f inverse prime, to find the derivative of f inverse, that's going to equal to 1 over f prime of f inverse. And we see that proven in a previous section, and it is essentially just using the chain rule. And so here we're going to go ahead and use that result to find the derivatives of the inverse trig functions. After all, that's what they are. They're inverses of some function that we already know. So here, theorem. Okay. We're going to begin with a differentiable function of x. So let u of x be a differentiable function. The way it's written, it's a function of x, clearly here. It's u of x. Okay, if that's the case, then the derivative with respect to x of the arc sine of u is equal to u prime over the square root of 1 minus x squared. Oops, sorry, that should be 1 over, that should be 1 minus u squared, not x squared. All right, so here, this derivative is equal to this. We actually have a few others here. The derivative with respect to x of the arc cosine of u is going to equal to almost exactly the same thing, except there's a minus here. So minus u over square root of 1 minus u squared, just like that. Okay. We have the derivative with respect to x of the arc tangent, and that's going to equal to u prime over 1 plus u squared. And the derivative with respect to x of the arc cotangent, I don't know how to spell, there we go, of the arc cotangent of u is going to equal to negative u prime over 1 plus u squared, like that. And the third set is going to be the derivative with respect to x of the arc secant of u is equal to u prime over the absolute value of u square root of u squared minus 1. And if you take the derivative with respect to x of the arc cosecant, that's going to be the same as this, except with a negative out in front. So minus u prime over absolute value of u square root of u squared minus 1. Okay. Note that most people don't ever bother memorizing all 6, or don't bother even recalling all 6. For the most part, if you remember these are the opposites. So sine, cosine, tangent, cotangent, secant, cosecant. The cofunctions are just the the derivatives of the cofunctions are just the negatives of the derivative of the regular functions. Right. So here, we're going to go ahead and prove just a couple of these. The proofs are very similar between one and the other. In fact, here the proof between this one and this one are almost identical, hence the very similar looking expressions. Here the only difference is this one will produce a negative, whereas this one doesn't. So the proof of this is, I'm going to go ahead and say this is a partial proof, because I'm not going to prove all of them. Let's start off with the first one, sine of u. So let's begin with just sine of, arc sine of x. Okay, so let's go ahead and find the derivative with respect to x of the arc sine of x. Okay, well, right here, the inverse derivative. Well, that's what I have here. This is an inverse function, and I'm trying to find its derivative. So here, let me rewrite this in a form that's a little more convenient. I'm going to write this as sine inverse of x prime. Now, that's saying the same thing. These are equivalent, and I'm taking the derivative. But now this looks exactly like this. This is an inverse function prime. Not that these mean anything different, but the notation now is sort of screaming at us. Hey, look, do this. Okay, well, that's going to be 1 over f prime. Okay, well, if f inverse is the arc sine, then regular f must just be the regular sine. So here, this is going to be sine prime of the inverse function. Not the derivative of the inverse function, just the inverse function. Okay, so that's going to be, well, the inverse function is the thing we started with. It's the thing we're trying to take the derivative of. So it's going to be the sine inverse of x. Okay? 1 over f prime of f inverse. Well, I know how to take the derivative of the sine function. That's the cosine function. So that's going to be 1 over the cosine of the sine inverse of x. Just like that. But now, I know how to do that. That's what we did up here. When we take sine of the inverse cosine, or in this case, cosine of the inverse sine, we're going to simplify this. Okay, so here, that's an angle. All right, well, what angle? Well, let's call it the angle y, just to keep it looking like the ones from before. Okay, so it's an angle situated inside of a right triangle. Here's my right triangle. Here's my angle y. And the sine of that angle y is going to be x, or in other words, x over 1. Well, the sine of an angle is the length of the side opposite of the angle divided by the hypotenuse. Now, here we can say that as being x over 1. So the length of the opposite side divided by the length of the hypotenuse, x over 1. And now by the Pythagorean theorem, I can fill in this third side. And in fact, it's the same one as we have up here. Even though we have a different function, here we have 1 as a hypotenuse, x is one of our sides, x is the hypotenuse, 1 is the hypotenuse, x is one of the sides, so then the remaining side must be this one. So here, by the Pythagorean theorem, we get that that's the positive square root of 1 minus x squared. Just like that. So now if I want the cosine of that angle, well, let's see, that's going to equal to 1 over the cosine of y, which is, well, let's see, the cosine is the length of the side adjacent to the angle. Okay, so it's this side right here. It's going to be 1 over the square root of 1 minus x squared. But then you have to divide by the hypotenuse. Right? The length of the side adjacent divided by the length of the hypotenuse. Okay, so divide that by 1. Oh yeah, but obviously dividing by 1 doesn't change anything. So here I don't have to write over 1. So here I can just write that as 1 over the square root of 1 minus x squared. Okay, so that tells me that the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. So now, by the chain rule, that means that the derivative with respect to x of the arc sine of a function of x is going to equal to 1 over the square root of 1 minus that function squared. But again, because of the chain rule, we now have to multiply that by the derivative of that function. Well, if the function, we don't know what it is. It's just called u. Okay, so then the derivative of u, we'll just call that u prime. Oh, but since these are being multiplied, u prime is like saying u prime over 1. So I can merge those together to give me u prime over the square root of 1 minus u squared. Oh, and that's what we were trying to prove. So this is the same as that. So that's the proof for that first one. So I'm going to ask you to try the second one, this one right here, the arctangent. So take a minute, go ahead and pause the video and do that. See if you can find, see if you can prove that the derivative with respect to x of the arctangent of u is equal to u prime over 1 plus u squared. The proof will look similar to this, but of course there's going to be some differences, otherwise you would get the exact same answer. So pause the video to give yourself as much time as you need, and once you're done, go ahead and unpause and we'll finish that together. All right, so let's take a look. We're looking to find the derivative with respect to x of the arctangent of x. We're going to start with that, and then once we have this derivative, we can use the chain rule to do it with a function instead of just a variable x. Okay, so here I can write this as the inverse tangent of x prime. Not that I have to, but this will make it look more like our previous formula, so make it look a little bit more familiar. So by our formula from before, the derivative of an inverse function is 1 over the derivative of the original function, not the inverse, just the original tangent. The derivative of the original tangent of the inverse tangent. Just like that. All right? That's this formula. F inverse prime is equal to 1 over f prime of f inverse of x. All right, well, the derivative of the tangent function, that's going to be secant squared. So here we can write that as 1 over secant squared of the inverse tangent of x. Just like that. And now we can go ahead and find what that is. Now remember, secant squared just means the secant of this, and then you square the whole thing. So I'm going to write that as 1 over secant of the inverse tangent of x. And then once you're done doing all of that, that's when you square. All right, so really we're just worried about this part. All right, so just like before, what is the inverse tangent of x? It's an angle. What angle? Well, this angle that I'm about to draw. It's the angle in a right triangle. I'm going to go ahead and call it y, but you can call it any label you like. It's this angle. Well, what angle? Well, the one I'm pointing at. Well, yeah, but what do I know about it? Oh, well, I know that if I take the tangent of that angle, I'm supposed to get x. That's the definition of the arctangent. The arctangent of y is an angle. Which angle? It's the angle whose tangent is x. Oh, okay. So here I can think of x as being x over 1. All right, so it's the angle whose tangent is x over 1. And remember, the tangent can be thought of as being the length of the side opposite of the angle over the length of the side adjacent to the angle. So this is the side adjacent. And now by the Pythagorean theorem, we can find that third side, c squared, the length of our hypotenuse squared, is equal to the x quantity squared plus the 1 quantity squared. And since 1 squared is just the number 1, we can write that as c squared is equal to 1 plus x squared. Right? You don't need to change the 1. 1 squared is still 1. Okay? So short side squared plus short side squared is equal to long side squared. Oh, but now we got to take the square root of both sides. So c is equal to plus or minus the square root of 1 plus x squared. Oh, but keep in mind, that's the length of a triangle. The length of a hypotenuse of a triangle. You can't have a negative length, so that must be positive. Okay, so now this is going to equal to 1 over the secant of y quantity squared. Oh, but going back to our basic trigonometry, we know that the secant of y can be thought of as the length of the adjacent, the length of the hypotenuse divided by the length of the adjacent side. Okay, so that's going to be 1 over, and again, secant of y can be thought of as the length of the hypotenuse divided by the length of the side adjacent to the angle y. And then don't forget the whole thing is squared. Well, here dividing by 1 doesn't change anything. So here we can just ignore the 1. So that's going to be equal to 1 over the square root of 1 plus x squared, and then the whole thing is squared. But here, we know that's got to be positive. So the square and the square root just cancel out. Since that's positive, we don't have to worry about positives and negatives here. We don't have to worry about the signs getting screwed up. We don't need to worry about absolute values or any of that. Here, the square root of 1 plus x squared squared will just give us 1 plus x squared. So that's going to be 1 over 1 plus x squared. So that's the derivative of the arctangent of x. So by the chain rule, if we want to take the derivative with respect to x of the arctangent of some function of x, well, that's going to be the same thing here, but instead of x, now that's the function of x. So that's going to be 1 over 1 plus u squared. But now by the chain rule, I have to multiply by the derivative of that inner function. So times u prime, which if I merge this all together, that's going to be 1 times u prime, that's u prime, over 1 plus x squared times 1, which just leaves us 1 plus u squared. And that's what we were trying to prove over here. The derivative of the arctangent is u prime over 1 plus u squared. U prime over 1 plus u squared. And I hope once you reach the end of that proof, you gave yourself some nice visual confirmation of, hey, yeah, I did a good job. For those of you who don't recognize this symbol here, QED is something that's traditionally put at the end of a proof that you make. This might be the first proof that you've proven. It's depending on what classes you've taken before. You might have proven something simple in Cal 1 or not. But these letters are traditionally put at the end of a proof. It stands for Quod est demonstratum. Quod, let's see, it should be erat I believe that's the correct spelling, or at least the correct Latin spelling. Quod erat demonstradum basically means that which was to be proven. Or in other words, here's what we were looking for. There are other versions of this which are used in different by different mathematicians or different textbooks and such. But this is just the one that I got used to many, many years ago. And it's just a nice visual confirmation of, hey, we got it. All right? So you'll occasionally see me use this throughout the course. If I haven't already, I think I probably already have. Just like when you're writing a composition, an essay, a letter, at the end of a sentence, you put a period. At the end of a proof, you put that symbol there. So that's the end of the proofs. We do have several others, but we're not going to worry about those. They all work exactly the same way. You begin by using this to find the derivative of the arc function of x. And then once you know the formula for the arc function of x, using the chain rule, you get the exact same thing for the arc secant of u, with u in place of x, and then u prime in your numerator, as we've seen a couple of times already. Right? So the rest of the proof is not particularly enlightening. We don't learn anything extra, so we're just going to go ahead and omit that. If anyone's curious, you can go ahead and try that yourself, and you should be able to, if you got this one, you'll get the other ones. All right, so let's take a look at some examples of using this. Example, let's start off simply. Let's say we want to find the derivative with respect to x of the arc, I don't know. Let's say the arc sine of 2x. All right, so here, given the formula we've proven over here, that's going to be u prime over 1 minus u squared under a square root. Okay, so that's your u right there. So u prime, the derivative of this, is going to be just the number 2. All right, that's your u prime, over the square root of 1 minus u squared. Over the square root of 1 minus, again, that's your u, and it's being squared. So now we can clean that up ever so slightly. That can actually be squared to give us 2 over the square root of 1 minus 4x to the second power. And there we go. That's the derivative of the arc sine of 2x. Okay. We can make things a little more complicated by giving this function something, making this function something a little bigger. Or we can make it a little more complicated by situating this function within another function. So let's say, for example, we want to find the derivative with respect to x of the arctangent of 5x over x squared. So now, yeah, we're going to have to use the formula we just derived, that we just proved, to find the derivative of the arctangent. But notice, that's only part of it. This is inside of a fraction, which means we're going to have to use the quotient rule on this. All right. So remember the quotient rule? The quotient rule says that we're finding the derivative of a quotient, that's the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the square of the bottom. All right. The bottom times the derivative of the top minus the top times the derivative of the bottom over the square of the bottom. Okay, well, several of these things are easy because they're just polynomials. We can leave that as x squared. We're going to have to figure that out. That's not automatic, but this one is nice and simple. The derivative of x squared is just 2x. That's going to be minus arctangent of 5x times 2x. So let me write the 2x in the front. Times the arctangent of 5x all over x squared squared. Well, that's just x to the fourth. Okay, so this is the only part that's not automatic. It's not the only part that we can do in our head because it's polynomial. So let's go ahead and go through that one. The derivative of the arctangent of u, again, we proved, was u prime over 1 plus u squared. Okay, so that's your u. So we're going to take u prime, which is just the number 5, over 1 plus u squared. Okay, so take that u and square it. Like that. So now we have a few things that we need to simplify. We can write this as, let's see here. We're going to need to give these a common denominator so we can merge that all together. So we can write this as 5x squared over 1 plus 25x squared. All right? 5 times x squared is up there. 1 plus, I went ahead and squared that out, minus 2x times the arctangent of 5x all over x to the fourth. Okay. Here, let me give these a common denominator. So let me divide this by 1 plus 25x squared and then multiply by 1 plus 25x squared. And now all of that has a common denominator, and with the common denominator, that denominator can be multiplied by that denominator. So now we can write this as one big denominator, namely x to the fourth times 1 plus 25x squared. That's going to be our new denominator. And our numerator is going to be 5x squared minus, if we distribute that, that's going to be 1 times that. Okay, that's just going to stay 2x times the arctangent of 5x. But now negative 2x arctangent of 5x times 25x squared will give us, oh, let's see, that's negative 50x to the third power times the arctangent of 5x. Okay? Let's see here. There are no like terms we can combine or anything of that nature. However, I do notice that x is a common factor for everything. So here, let me say, well, look, if I divide this term by x, that x goes away. If I divide this term by x, the x squared just becomes x. And if I divide this term by x, the x to the third becomes an x squared. But whatever you do on the bottom, you have to do the same thing on top, right? So here, I divide this bottom by x, and this x to the fourth will become x to the third. So in the end, our result is Let me go ahead and put these in descending order. Well, you know, that's fine. I can write that as 5x minus 2 arctangent of 5x minus 50x squared times the arctangent of 5x. And then all of that is divided by, here, let me distribute x to the third times 1 is x to the third. And x to the third times 25x squared is 25x to the fifth. And I'm glad I'm done because that's the end of my paper. So that is our result. Don't forget, just because we're learning new techniques for differentiation and in later sections integration, that doesn't mean any of our old ones go away. The product rule, the quotient rule, the chain rule, those don't go away. They're simply supplementing these new ones. So go ahead and give this a try. All right, let's go ahead and have you find the derivative of we're going to have x square root of 4 minus x squared. Notice that doesn't involve an arc function at all. That's just a product rule. No? Plus, oh, I'm sorry, I forgot a 2 here. So that's being divided by 2. Plus 2 times the arc sine of x over 2. So go ahead and give that a try. Pause the video and give yourself as much time as you need. Go through and find the derivative. Once you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. That's a product rule. Okay, so I'm going to take the derivative of the first part times the second part. Plus, now I need to take the derivative of the second part times the first part. Okay. Plus, and over here I need to take the derivative of all of this. Okay. Now, I know that if I take the derivative of something times a number, I can just factor that number out, right? Derivatives are linear operations, so the derivative of 2 times something is the same as 2 times the derivative of that something. So let me just pull that 2 out so it doesn't bother me anymore, or at least not for a while. Okay, so now let's see if we can find these derivatives. All right, well, that first one's nice. The derivative with respect to x of x over 2 is now just 1 over 2 times that square root. In fact, let me write that up here. 4 minus x squared. Okay, plus, now here, I want to take the derivative of this. Whenever I take the derivative of a square root of something, I end up with 1 over 2 times the square root of that same something. All right? The square root of something has a derivative 1 over 2 root of that something. But because of the chain rule, I now need to take the derivative of that something and multiply it in. Okay, so the derivative of this, that's 0, and the derivative of minus x squared, that's minus 2x, times that x over 2 that I had already, plus 2. The derivative of the arc sine of x over 2, we see from our previous result, is going to be the derivative of that argument over the square root of 1 minus that argument squared. Okay, so it's going to be the derivative of x over 2, which is just 1 over 2, over the square root of 1 minus that argument squared. Like that. Okay, so that's all the calculus. So now we have some algebra to simplify here. So let's see what we can't simplify. All right, well, let's see. First of all, these 2's divide away. And here, half of 2 divides away. All right, so far we have square root of 4 minus x squared over 2 plus my numerator is x squared over my denominator is 2 times that square root plus 1 over, right, these two divide away, gives me just 1, over square root of 1 minus, here let me actually square that, x squared over 2 squared is 4. Okay. I know that I can go ahead and simplify that by giving them a common denominator. I can write this 1 as 4 over 4. Okay, so now I can actually put those together. I also notice that these two almost have a common denominator. If I just multiply that by the square root of 4 minus x squared here on top and bottom, so let me go ahead and do that as well. Square root of 4 minus x squared, square root of 4 minus x squared top and bottom. Okay, so right here, that's going to be, well, square root of 4 minus x squared times itself. Or in other words, square root of 4 minus x squared squared. Well, then the square and the square root are going to go away, and I'm just left with 4 minus x squared plus x squared over the common denominator, because now I have a common denominator. So this numerator plus that numerator over my common denominator, 2 square root of 4 minus x squared. And I notice here now these subtract away. So those are gone. X squared minus x squared. Over here, I can write that as 1 over the square root of, well, that's 4 minus x squared over 4. But notice I know how to take the square root of 4. So here I'm writing this as 4 over 2 square root of 4 minus x squared. Those are gone now. I'm not going to bother writing them anymore. Plus 1 over the square root of 4 minus x squared over 2. Here, I took the square root of the top. Okay, well, I just write it as the square root of the top. But now taking the square root of the bottom, I can actually do that. And now I'm dividing by a number that's the same as multiplying by its reciprocal. So here I can write that as 4 over 2 square root of 4 minus x squared plus 2 over square root of 4 minus x squared. Just like that. I notice right here these two simplify. 4 over 2 is the same as 2 over 1. So now I'm left with 2 over square root of 4 minus x squared plus another 2 over square root of 4 minus x squared. And since they have a common denominator, I can merge their numerators as 4 over the square root of 4 minus x squared. Okay. And just a quick review, let's see here. So now we can, oh, I seem to have made a mistake right here. When I multiplied these together, I said x times x is x squared. That should be negative x times x. So that should be a negative x squared. Oh, that doesn't change very much. Here, that plus x squared should be minus x squared. So here, instead of canceling out, they double up. So that's going to be minus x squared minus another x squared is minus 2x squared. Okay, so that doesn't change too much, thankfully. Let's see here. Negative x times x is negative x squared. So I have a negative x squared from here. Another negative x squared, so that's negative 2x squared. Yeah, that's right. So now when I divide those out, that's going to be 4 minus 2x squared. If I divide that by 2, I get 2. If I divide that by 2, the 2 just goes away on me. So now I have 2 minus x squared plus another 2. So the 2 plus 2 still give me 4, but now I have minus x squared. There we go. My apologies. I dropped the negative here. Okay, so now we can rationalize that. Note that the denominator is got a radical. I can rationalize this by just multiplying it times itself, top and bottom. Here, the square root of 4 minus x squared times the square root of 4 minus x squared is the square root of 4 minus x squared quantity squared. And that quantity squared and that square root come together to give me just my argument. So here that denominator is just going to become 4 minus x squared without a square root. And now these are going to give me 4 minus x squared times the square root of 4 minus x squared. And now you notice that those two divide away, which makes us happy. So in the end, we get a result of the square root of 4 minus x squared, and that's it. That is the derivative of all of this is going to give us that expression right there, which incidentally, if you think toward the future, what does that mean? Well, if the derivative of all that stuff is that nice little expression, that means the antiderivative of that nice little expression will be that big hulking thing right there. So in the next section, we'll see some problems like that, where we're going to start off with something like this, and instead of looking for a derivative like we do in this section, looking for an antiderivative will result in expressions that involve arc functions, inverse trig functions. But that'll come by in the next section. For now, that is our result. For our last example, let's take a look at something that sounds like a question from Cal 1, but that now uses one of these new kinds of functions. The question is, let's go and find the equation of a tangent line. Find the equation of the line that is tangent to the graph of, let's say y equals negative 1/4 times the arc cosine of x at the point negative 1/2 comma negative pi over 6. Okay. In fact, you should be able to do that based off of what we've talked about. So actually, you might try that. You might pause the video and go through this. Remember to find the derivative of the function. That'll give you the slope of the line tangent to it. And then using this information, you can find the slope of the line tangent at that particular point. And finally, you'll have a slope and a point, and you can make your equation of your tangent line. So if you have the desire to, go ahead and pause the video and find the equation of that described tangent line. And once you're done, go ahead and unpause and we'll finish it together. All right, so let's go ahead and find a derivative. We want to find y prime. Okay, and remember we have that the derivative of the arc cosine is negative u prime over 1 minus u squared. But in this case, u is just x. Okay, well, x prime will be 1. So here, this is just going to be the number 1. So we're going to have minus 1 over the square root of 1 minus u squared, or I guess x squared. That negative 1/4 is just going to stay as it is. So we're going to end up with negative 1/4 times negative 1 over the square root of 1 minus x squared. So that's the derivative of our function. Here we can clean that up ever so slightly, I suppose. We can write that as a positive 1, negative times a negative, 1 over the 4 square root of 1 minus x squared. Okay, so there's our derivative. So now we can substitute in this x value in here to find the slope at that particular point. So this is the slope of every tangent line. So the slope of the line tangent at negative 1/2 comma negative pi over 6 is going to be m, symbol for slope, like back in algebra, is equal to 1 over 4 square root of 1 minus, we're going to take our x value, squared. All right, so let's go ahead and do that. That's going to be 1 over 4 square root of 1 minus. If you take negative 1/2 and square it, that's positive 1/4. Okay, 1 minus 1/4 is 3/4. Take the square root of 3/4. That's going to be root 3 over 2. And now these reduce away, and I'm left with 1 over 2 root 3. All right, so that's my slope. Let me rationalize that. We don't want any radicals in our denominators. So that's going to give me root 3 over, let's see, root 3 times root 3 is root 9. So that's just 3 times 2 is 6. So there we go. There's our slope, root 3 over 6. And now we can go ahead and find the equation of our line. Remember, the equation of a line can be found using equation of a line with slope m through the point x1 comma y1 can be given by y minus y1 equals m times x minus x1. And we have all of that information now. Y minus y1, okay, well that's negative pi over 6, equals m, which we just found as root 3 over 6, times x minus x1, which we see as negative 1/2. We can simplify all that out. That's y plus pi over 6 is equal to root 3 over 6. Let's see, that's going to be x plus 1/2. We can distribute that, which will give us y plus pi over 6 equals root 3 over 6x plus root 3 over 12, once we multiply those. And finally, if I subtract pi over 6 from both sides, that's gone. Here I can give these a common denominator by multiplying top and bottom by 2, and my tangent line is going to be y equals to, that's an inappropriate use of an equal sign, isn't it? It should be that gives us, that implies. Y is equal to the square root of 3 over 6 times x plus root 3 minus 2 pi over 12. And there we go. All right. And that brings us to the end of our section. If anybody has any questions, comments, or problems, please make a note of those. Make sure you write those down because it's very easy to forget what question one has or exactly how that question should be worded. So as you have them throughout the section, go ahead and make sure you write those down and let me know next time we meet during office hours, during our next class session. And I hope everyone has a nice day.